Hi everyone, this is Mr. Zimmerman. Today we're going to work on the section 2-1 notes. I'd like to make a quick thank you to Miss Barber for doing the chapter 1 notes. And what I'd say about chapter 2 is going to be different, okay? It's about logic and reasoning. We will use some of your geometry things that you learned in chapter 1 and some of the algebra things that you already know in chapter 2. But it will definitely be different. So let's go ahead and start with this definition that we have right up here. And what we're looking at is inductive reasoning. So with inductive reasoning, we're going to try to make a guess, an educated guess of what we think may be true. That's called a conjecture. Okay? So that conjecture is going to be based either on specific cases or examples or on a pattern. So let's go ahead and start looking at example 1. So for example 1, we have 4 problems where we have to describe the pattern and then we have to find the next item in each pattern. So looking at number 1, I'm going to do a verbal description of what the pattern is, and then I will write down what the next item is. So what you can see I did here is I rewrote the fraction 1/2 as 2/4, and I wrote the number 1 as 4/4. So I have everything written in fourths. So then you should be able to see the pattern is that you add 1/4 to get from one item to the next. So if we have 1/4, 2/4, 3/4, 4/4, the next item in the pattern should be 5/4. So you can see here that the next item in the pattern is 5/4, which you could also write as 1 1/4. Okay, well let's move on to number 2. And some of these, I really can't show you a method. You just have to think and try to figure out what the pattern might be, and a lot of that just comes with experience, the more and more that you do. So what you have in number 2 is you want to notice that all of these numbers are perfect square numbers. You can see that I've written 100 as 10 squared, 81 as 9 squared, 64 is 8 times 8, and then 49 is 7 squared. So then the next item in our pattern should be 6 squared. So again, our answer for the 5th item in the pattern is 6 squared, which is equal to 36. Don't feel bad if you didn't recognize this pattern. Again, this type of reasoning, a lot of it just comes with experience. Let's move on to number 3 in example 1. So I've noted what the pattern here is. To get from the first item to the second item, you're going to add a row with 3 dots. And then to get from the second item to the third item, you're going to add a row with 4 dots. Well, that means I should probably add 5 dots. So I'm going to add a row with 5 dots to get the next item in the pattern. So you can see I drew the next item in the pattern for you. So the 4th item, the 3rd item has 10 dots. And then if I add 5, or if I add a row with 5 dots, the 4th item will have 15 dots. All right, moving on to number 4 in example 1. If I'm looking for the 5th item in this pattern using inductive reasoning, I think you can see here that first they divided the square into 2 equal pieces, and then they divided this top rectangle into 2 equal pieces, and then they divided this square in the upper left, they divided into 2 rectangles, two rectangles that are the same. So then let me move over here and I'll draw you the fifth item in the pattern. So you can see that I divided this rectangle on the upper left right here into two squares that are the same. So I guess if I had to describe this pattern, I'm dividing a square in two, then a rectangle in two, then a square in two, then a rectangle in two, and so on. All right, let's move on to example 2. In example 2, we have number 5, and what we're going to do is we need to use our inductive reasoning to make a conjecture to fill in the blank. All right, so we're going to try to come up with a conjecture of what we believe may be true. So we're going to make up a couple of specific examples to see what's going on and see if we can figure out what would be true. That would be our conjecture. So what I've drawn for you here is number 5 says that if we double the side length of a square, so you can see here I've got a square where all the sides are of length 3, and then I doubled the length of those sides to where I have a square with all the side lengths would be 6. All right, then you have to remember what perimeter is. So the perimeter of the first square, we add up all the sides. So it'll be 3, 3, 3, and 3. So that's going to give us a perimeter equal to 12. And then the side lengths on the second square after I doubled them are 6, 6, 6, and 6. So then that perimeter would be 24. And so it looks like when I doubled the length of a side, it also doubled the perimeter from 12 to 24. Now we might want to do this with one more specific example just to see if that holds true. So I'll draw you another one really quick. So in my second specific example, I've got a square where all the sides are 5. So I'm going to add up the 4 sides. So 5 plus 5 plus 5 plus 5. That's going to give me a perimeter of 20. And then I double the side lengths to 10. And so all the side lengths are 10 on my second square. So if I add all 4 sides together, it's going to be 10 plus 10 plus 10 plus 10. And my perimeter is going to be 40. So you should be able to see by looking at these two examples that using our inductive reasoning, it looks like if we double the length of a side, then the perimeter of the square is also doubled. So you can see I filled in the blank on number 5 that our conjecture is the perimeter of the square is doubled. Now let's take a look at number 6. So let me draw you a few examples of what number 6 would look like. And we have to draw some lines that, if you read this part right here, we need some lines that intersect at a point. So I'll give you a second to, I drew 3 specific examples for you. So I'll give you a second if you want to draw a couple of the examples. The important idea here is that n represents the number of lines. So you should see in my first example over here that I've got 2 lines, and then in my second example n is equal to 3, well then I have 3 lines. So then the non-overlapping angles here that we're talking about, those would be these angles right here. So you'd have this black angle, and then this blue angle, and this red angle, and this green angle. So in that case, we have 4 angles. So again, in this first case over here, or this first specific example, I've noted for you that we have n equals 2 lines, and then we have 4 non-overlapping angles. Now let's look at the other, or the second case where the number of lines is equal to 3. So in the second example, we have 1, 2, 3, 4, 5, 6 non-overlapping angles. And in the last case, we have 1, 2, 3, 4, 5, 6, 7, 8 non-overlapping angles when the number of lines is 4. So again, just to wrap this one up, when n is 2, the number of non-overlapping angles is 4. When n is 3, there is 6 non-overlapping angles. And when n is 4, there's 8 non-overlapping angles. So then our conjecture is going to be that the number of angles, non-overlapping angles that are formed, is twice the number of lines. So our conjecture is that we're going to fill in the blank with a (2n) is our conjecture for number 6. We fill in the blank with 2n because we can see that the number of non-overlapping angles formed is twice the number of lines, n. Now let's take a look at number 7. So let's zoom in on number 7. We have 4 figures where these figures are made up of these small triangles that all have a side length of 1. Now again, this is about perimeter, so you got to remind yourself that perimeter, like for example on the third figure, if we want the perimeter, we have to add up the lengths of the sides that go around the outside of the figure. So we'd have 1 plus 1 plus 1 plus 1 plus 1. And you can see the perimeter of that one is 5. And then down here I noted how many of these triangles are in each figure. So this first figure has 1 triangle. The second figure has 2 triangles. The third figure has 3 triangles. And the fourth figure has 1, 2, 3, 4 triangles. So then the pattern that we're trying to look for here is we're trying to relate the perimeter to the number n, the number of small triangles. Okay? So in this one, n represents the number of small triangles. So you can see when there's 1 triangle, the perimeter is 3. Well, that's 2 more than the number of triangles. And then in the next example, we've got a perimeter of 4. That's 2 more than the number of triangles. And then the third one, we've got a perimeter of 5, which is 2 more than 3, because we have 3 triangles. And then in the last example, we can see that when we have 4 triangles, 2 more than that is 6, right? 4 plus 2 is 6. So it looks like the perimeter is always 2 more than the number of triangles. Well, that will make our conjecture n plus 2. Again, the reason we have that is n represents the number of the small triangles. If we add 2 to that, it'll tell us our perimeter. Okay, so to wrap up number 7, again, one last time, you just take the number of triangles and add 2, and that will tell you the perimeter. Now let's flip to the next page. And let's zoom in on this definition of a counterexample up here at the top of the page. Okay, so in geometry, when we make a conjecture, it is either true or false. All right, if it's true, it's always true. If there's one case where it's false, then it's false. So if you can find that one example that shows that your conjecture is false, that's called a counterexample. And it proves that your conjecture is false. So let's take a look at number 8. Before I go on with number 8, in example 3, I'd like you to note that all of the problems for example 3, that's number 8, 9, 10, 11, and 12, all of these conjectures are false. All right, they're telling you that they're false. So we need to find one example, our counterexample, that proves the conjectures are false. Notice that I've highlighted the if part of the statement in red. That's 3 lines lie in the same plane. And then I've highlighted the then part of the statement. They intersect in at least one point. I've highlighted that in green. So what our counterexample will need to do is it'll need to make the if part true and the then part false. So our counterexample will need to make the red part true and the green part false. Now our counterexample could be a picture, it could be a number, it could be a word. Okay, it's anything that makes the red part true and the green part false. I'll give you a second to draw the picture that I drew. And then what you should notice in my picture is that it makes the red part true. You have 3 coplanar lines, but it makes the green part false because they do not intersect at all. In fact, there are 3 parallel lines. So in this number 8, my counterexample is actually going to be the figure that I drew for you. Now let's look at number 9. You can see that I've already highlighted the statement. Again, we've got to come up with a counterexample that makes the red part true and the green part false. So you might read the beginning of this statement right here, and you might say, oh, well, they're collinear, so they're all on the same line. So you might be tempted to draw a figure that looks something like this. So you may have drawn a figure like I've sketched here for you, and you'd say, well, that looks like what we were talking about in chapter 1 when we were talking about the segment addition postulate. That looks good. But please note, when you look at this first part of the statement right here, it says nothing about the fact that G has to be in between A and N. It just says they all have to be on the same line. So it doesn't have to look like that. So it could look something like this. This example, if you look at it, it definitely makes the red part, it makes this part true. The distance from A to G is 7, and the distance from N to G is 5. Well, if that were the case, then the distance from A to N would have to be 2. Well, certainly that is not 12. All right, so again, my figure is going to be my counterexample. And again, it makes the red part, it makes this true, but it makes this part false. All right, so again, it makes the red part true and it makes the green part false. So my counterexample is that AN is equal to 2. Now let's look at number 10. I've highlighted the if part in red and the then part in green. So let's look at a specific example. Let's make something up and see what happens. The example I made up, I said, well, let's first of all, x and y can be any real numbers. So I just chose x equals 5, y equals 2. And you can see that when x is 5 and y equals 2, then the red part is true, 5 is greater than 2. And then the green part, 5 squared is greater than 2 squared, which gives you 25 is greater than 4. That's also true. So you're thinking, oh, well, I guess this conjecture is true. But remember, if we can find one example that shows that the red part is true and the green part is false, then we've proved the conjecture is false. And that's our counterexample. So let's try something else. Here we're looking at another specific example. This time I said, again, x and y can be any real number. So this time I said, let's have x be -3 and y be -6. And then the red part of our statement here is still true because -3 is greater than -6. If you think on the number line, -3 is to the right of -6, so it's greater. But then if I plug the -3 in for the x and I plug the -6 in for the y and I square them, then I get a statement that says, well, -3 squared is 9 and -6 squared is 36. Well, now this says 9 is greater than 36. Well, that is false. So my counterexample is right here. That's one case where x and y are real numbers that make the red part of the statement true and the green part of the statement false. So that is my counterexample. This proves that my conjecture in number 10 is false. Now let's take a look at number 11. In number 11, I've drawn 3 arcs here that show 3 non-overlapping angles. And I've listed them over here on the left. So I have angle ABD, that's the blue angle. I have angle DBE, that's the red angle. And I have angle EBC, that's the green angle. So those are 3 non-overlapping angles. But there's other angles in this figure. So for example, I could mark this black angle that goes from here all the way to there. Well, that would be angle DBC. Well, right there, this list of angles is my counterexample. My statement in number 11 says that the total number of angles in this figure is 3. Well, right here, I've just listed 4 angles in that figure. And that right there proves that that conjecture in number 11 is false. Now let's take a look at number 12. Again, I've highlighted the if part in red and the then part in green. So we want to make a counterexample that shows that the red part is true and the green part is false. I've written down the measures of 2 acute angles. A 40-degree angle, that's definitely less than 90. That's our definition of acute. And a 30-degree angle, that's also less than 90. So the conclusion of our statement here in green says the sum of these 2 angle measures, if we add them together, it should be the measure of an obtuse angle. But you can see right here that if I add these 2 angles together, I get 40 degrees plus 30 degrees, that's 70 degrees. Okay, 70 degrees is not obtuse. All right, to be an obtuse angle, the measure has to be greater than 90. And technically less than 180, but definitely 70 here is not greater than 90. So then my counterexample for this one is right here. All right, the measure of angle 1 equals 40, and the measure of angle 2 is equal to 30. All right, so wrapping up number 12, again, we have 2 angles. They both have to be acute. There they are. And they definitely make the if part true and the then part false. So that is our counterexample that proves that the conjecture in number 12 is false. All right, we've only got 2 to go, so we're almost done. So let's look at 13 and 14. All right, in 13 and 14, we need to decide whether the conjecture is true or not. Okay? If it's true, then we just write true. But if it's false, then we need to make a counterexample. So let's look at 13 first. I've drawn 2 points for you, just kind of randomly. And the conjecture in number 13 is that Q and R are collinear. Well, if you remember, I think it's on the first page of your Chapter 1 note packet, there's a thing called the line postulate. And again, postulates, we accept them as true facts. And that postulate says through any 2 points, there is exactly one line. So if I draw the line here, you can see that this one is true. All right, only one to go. So let's look at 14. Again, we're going to decide whether this one is true or false. If it's true, it's just true. If it's false, then we have to come up with a counterexample. We need one example that makes the if part true and the then part false. Again, I've highlighted the if part true in red, and I've highlighted the then part in green. So if this is going to be false, we'll need to make the red part true and the green part false. All right, first thing I want you to note on this is that it says J is between H and K. All right? So if it's between, they're definitely collinear. Okay, all 3 points are on the same line. And it could look something like this. So I've drawn you a picture here. And have I satisfied the if part of this, the red part? Certainly, J is between H and K. And then it looks like, well, I've got these marked here. It looks like the distance from H to J is equal to the distance from J to K. But you have to read this red part a little more carefully. Again, it says J is between H and K. It doesn't say anything about J being exactly in the middle right here, that it's the midpoint between H and K. So I need to erase this. If it looked like that, it was true. But all I need to do is satisfy this red part. So let me redraw this for you. Here's my new drawing. And my new drawing, you can see it definitely satisfies this red part. It makes the red part true. It's J is between H and K. So they're definitely all on the same line. But J is just somewhere in between H and K. It's right here. It does not have to be right in the middle. And then you can see now that the distance from H to J is 10, and the distance from J to K is 4. So these are not equal. So that picture, again, is my counterexample. It makes the red part true and the green part false. So that conjecture in number 14 is false. Here is my counterexample then for number 14, which proves that that conjecture is false. And that wraps up our lesson for lesson 2-1. So thanks for watching, and I'll see you soon in class. Thanks. See you guys. Bye.